At first, the warning looked harmless. A weak disturbance near the Gulf, low odds, cautious language, nothing worth fearing. But behind that quiet forecast sat a name meteorologists cannot use again. Andrew. The storm that nearly vanished before becoming a Category 5 disaster exposed how quickly confidence can collapse. In 2026, scientists were not watching Andrew return. They were watching something more unsettling, how a coastline reacts when the first signal looks too small to matter. So what did they really detect? And why could the worst part arrive before the storm even has a public name yet? The name that could not return. The first thing visible on the satellite image was not a hurricane. It was only a disturbance, a pale, disorganized smear of clouds over the southern Gulf, pressed against the warm water of the Bay of Campeche and the curved coastline of eastern Mexico. There was no clean eye, no circular wall of thunderstorms, no official cone extending toward Florida. At the National Hurricane Center in Miami, the public wording on the morning of June 10, 2026, was restrained. A broad area of low pressure could form late in the week. Conditions were not expected to be favourable for significant development. The chance of tropical cyclone formation through 48 hours was near zero. Through 7 days, it was 10%. That should have made the situation feel ordinary. Early June often produces weak rain-heavy disturbances in the Western Caribbean or the Southern Gulf. The atmosphere is still transitioning from spring into summer. Wind shear can tear apart a circulation before it ever earns a name. Dry air can enter from the north. Land can interrupt the low-level centre before it has time to stack vertically. On paper, the system was barely a system at all. But the name attached to the public conversation was not ordinary. Andrew. That detail matters because Andrew was not on the 2026 Atlantic naming list. The first name of the season was Arthur, then Bertha, then Cristobal, Dolly, Edward, Faye, and the rest of the rotating list selected for the basin. Andrew could not appear there because Andrew had been removed from future use after 1992. It belongs to the category of names that meteorology does not recycle, not because the atmosphere remembers them, but because people do. The question, then, is not whether scientists detected a literal 2026 Hurricane Andrew forming. They did not. The question is why 1 week early season signal was being compared to the storm that changed modern hurricane preparedness. To understand that comparison, you have to go back to another quiet beginning. On August 14, 1992, a tropical wave left the coast of Africa and moved west over the tropical Atlantic. It did not look like a historic disaster at first. Satellite analysts watched the convection struggle. The system became a tropical depression on August 16th and Tropical Storm Andrew on August 17th. But then it weakened, fought unfavourable winds and nearly disappeared on August 20th. For several days, Andrew was a name on a map that did not yet deserve fear. That is the part of the story that is often forgotten. Andrew did not begin as an obvious catastrophe. It began as a poorly organised disturbance that survived long enough for the environment around it to change. The significance of that detail was not obvious at the time. Once Andrew moved into better conditions, the storm strengthened rapidly. It became a hurricane on August 22nd. 24 hours later, it was a Category 5 hurricane. By the afternoon of August 23rd, it had reached peak winds near 175 miles per hour and a minimum central pressure of 922 millibars. It crossed the Bahamas, regained Category 5 strength, and struck Elliott Key and then the Homestead area of South Florida on the morning of August 24th. 2 days later, it reached Louisiana as a Category 3 hurricane. The official track is clean on paper. The human geography was not. South of Miami, neighborhoods were stripped down to slabs and frames. Roofs were peeled open, warehouses collapsed, mobile homes disintegrated. In Dade County, whole blocks lost the ordinary markers that allow a person to recognize where they are. Street signs, trees, fences, storefronts, the small visual anchors of everyday life were torn away. The old National Hurricane Center office in Coral Gables survived, but the storm exposed how vulnerable the institution itself could be when the atmosphere it studied arrived at its own door. Andrew was not simply a weather event. It was an audit of buildings, forecasts, emergency management, insurance, construction codes, evacuation behaviour, and public memory. That is why the comparison still carries weight in 2026. The worst part is not that a confirmed Andrew-like hurricane is forming. As of the morning outlook, no such storm existed in the Atlantic. The worst part is that the conditions surrounding hurricane risk can look calm at the exact moment the public begins to relax. NOAA's seasonal outlook for 2026 leaned below normal. The agency gave a 55% chance of a below-normal Atlantic season and forecast 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. El Niño was expected to develop and intensify during the season, a pattern that often increases upper-level winds across the Atlantic and suppresses tropical cyclone formation. That sounds reassuring until you look closely at what the outlook does not say. It does not say where storms will form. It does not say where they will make landfall. It does not say whether one of the few hurricanes will find a narrow corridor of warm water, low shear, and high ocean heat content close to shore. Hold that thought, because this is where Andrew becomes less of a name and more of a warning label. The 1992 Atlantic season was not remembered because it produced a long list of storms. It was remembered because one storm found the right window and moved through it quickly. A quiet season can still contain a catastrophic landfall. A low probability disturbance can still become the first entry in a chain of decisions. A 10% circle on a tropical outlook can still force meteorologists to watch the next model cycle, then the one after that, because early tropical systems are often judged not by what they are, but by what the surrounding atmosphere might allow them to become. The Bay of Campeche disturbance did not need to become Andrew to matter. It needed only to remind forecasters of the asymmetry between public attention and scientific caution. Scientists do not name ghosts. They measure pressure falls, wind shear, sea surface temperatures, vorticity, moisture, steering currents, and model spread. The public often measures something else: resemblance, a cloud mass in the wrong place, a year that feels unstable, a historical name returning in headlines even when the naming system itself forbids it. So the opening fact is not dramatic, but it is revealing. On June 10, 2026, the Atlantic did not contain Hurricane Andrew. It contained a weak possibility in the southern Gulf, a below-normal seasonal forecast, a retired name that could not return, and a coastline that had learned once before how quickly ordinary language can fail. The first official signal was small. The larger danger was not in the cloud field itself. It was in the assumption that small signals cannot become consequential. The forecast that made people relax. Seasonal hurricane forecasts are written in the language of restraint. They do not arrive with sirens. They arrive as probabilities, ranges, climate signals, confidence intervals, and carefully chosen verbs. A press release is published, a chart is displayed, a number appears beside the phrase below normal, and for many people along the coast, that number becomes the only part that remains in memory. In May 2026, the forecast gave the Atlantic a 55% chance of a below normal season. The expected range was 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. Those numbers sat below the long-term average, and the reason was familiar to forecasters: El Niño. When El Niño strengthens in the tropical Pacific, it often changes the wind patterns over the Atlantic. Upper-level winds become less forgiving, vertical wind shear increases. Thunderstorms trying to wrap around a developing tropical center can be pushed out of alignment before the circulation has time to organize. On the surface, that sounded like relief. In coastal offices from Texas to the Carolinas, emergency managers could point to the outlook and say the year was not expected to behave like the most violent years of the previous decade. Insurance analysts could build models around lower accumulated cyclone energy. Local news stations could run graphics showing a calmer basin. Hardware stores could still stack plywood near the entrance. But the urgency in the public mind was different. Below normal is not the same as safe. But in ordinary language, it feels that way. That is where the forecast became more complicated than the headline. NOAA's own outlook included the warning inside the fine print: seasonal prediction cannot tell a community whether a hurricane will come ashore there. It cannot predict landfall location months in advance. It cannot say whether one storm will find the one corridor where the shear relaxes, the ocean heat deepens, and the steering flow points toward a populated coastline. The seasonal forecast is a basin-wide estimate. Disaster is local. The distinction matters because hurricanes do not damage averages. They damage roofs, bridges, hospitals, substations, ports, mobile home parks, and barrier islands. A below-normal season with one major landfall can produce more loss than a busy season filled with storms that curve harmlessly into the open Atlantic. A number that describes the basin cannot describe a family standing in a hallway at 3 a.m, while pressure changes make the walls breathe. Andrew proved that point with unusual clarity. The 1992 season did not need to be crowded to become historic. It needed one storm to survive long enough, intensify fast enough, and cross the wrong piece of coastline at the wrong hour. By the time Andrew reached South Florida near Homestead on August 24, 1992, it was a Category 5 hurricane with winds near 165 miles per hour. The eye moved over a landscape of subdivisions, shopping centres, schools, farms, and military installations. The storm's compact size made some people outside the core underestimate it, but inside the eye wall the destruction was concentrated and severe. Forecast offices had tracked Andrew, aircraft had sampled it, satellites had watched it strengthen. The failure was not that science did not see the storm. The failure was that a modern urban region discovered how much of its built environment had been permitted, inspected and trusted under assumptions the wind did not respect. Afterward, the conversation changed from meteorology to construction. Roof connections, window protection, garage doors, mobile homes, code enforcement, and the fragmented building standards of Florida became part of the hurricane story. Andrew was not only a weather disaster, it was a structural examination carried out by air moving faster than officials had imagined would arrive at scale. That historical memory sits behind every calm forecast. When a season is described as below normal, the atmosphere is not promising mercy. It is only saying that the large-scale environment may suppress some storms more effectively than usual. Suppression is not elimination. El Niño may raise shear across the main development region, but the Atlantic is not uniform. The Gulf of Mexico can behave differently from the eastern tropical Atlantic. The Caribbean can briefly become favourable even when the basin as a whole looks hostile. A disturbance does not need the entire ocean to cooperate. It needs a window. Early June is a revealing time for that reason. The main development region between Africa and the Caribbean is usually not at its seasonal peak. The strongest Cape Verde hurricanes more often belong to August and September. Yet the Western Caribbean, the Bay of Campeche, and the Gulf can produce early season mischief, not always through classic long-track hurricanes, but through messy systems with heavy rain, poorly defined centres, and uncertain futures. They can sit near land before models agree on whether there is anything there. They can flood first and organise later. They can appear unimpressive on the first advisory and then become operationally difficult because they are close to people. That was the frame around the weak Southern Gulf signal in June 2026. It was not a hurricane, it was not Andrew, it was not even a named storm. The official language remained low confidence and low probability, but because the season had been sold to the public through a below normal headline, the disturbance exposed the weakness in how people receive forecasts. Many hear below normal and translate it into fewer reasons to prepare. Meteorologists hear below normal and translate it into a distribution of possible outcomes, some of which still contain landfalling hurricanes. The difference between those interpretations is not academic. It determines whether generators are tested before the power fails, whether evacuation routes are understood before traffic slows, whether medications are refilled before pharmacies close, and whether local officials communicate risk before a cone appears. Preparedness is rarely cinematic. It looks like quiet errands, boring checklists, and decisions made before fear supplies the energy. So the 2026 forecast did not create the danger. It revealed a communication problem that has existed for decades. Scientists were not telling the public there would be no threat. They were describing a season shaped by El Niño, competing Atlantic warmth, and uncertainty that increases with distance from the present. The public, however, tends to flatten uncertainty into mood. Below normal becomes calmer. Calmer becomes less urgent becomes delay. That is the part Andrew still explains. The storm is remembered because of what it did, but its deeper warning is what it exposed before landfall was even complete. Catastrophe does not require a historically active season. It requires vulnerability lined up beneath one efficient storm. In 2026, the worst part was not a confirmed monster on the map. The worst part was how easily a quiet forecast could make the coast lower its guard before the atmosphere had shown all its options, the small storm that found the gap. Before a tropical cyclone becomes a name, it is a negotiation between water and air. The water supplies heat. The air decides whether that heat can be organised. Along the western edge of the Yucatan Peninsula, where jungle gives way to mangrove and shallow coastal shelf, that negotiation was beginning in its weakest form. A tropical wave was moving west. A broad area of low pressure could form. The National Hurricane Center placed the location over the Bay of Campeche and assigned the system a 10% chance of development through 2 days, and the same 10% through 7. No one looking at that advisory could honestly call it alarming. The wording was careful, almost dismissive. Environmental conditions were only marginally conducive. The system was expected to move inland over eastern Mexico by late weekend. In operational hurricane language, that is not the sound of a monster being declared. It is the sound of forecasters keeping a small door open because the atmosphere had not yet closed it. The Bay of Campeche has a particular way of making small doors matter. It is not an open ocean nursery like the deep tropical Atlantic east of the Lesser Antilles, where long-track storms can spend days gathering structure over thousands of miles. It is a pocket of warm water tucked beneath Mexico, bordered by the curved coast of Veracruz, Tabasco, Campeche and the Yucatan. Systems forming there do not always have room. They can become rainmakers before they become cyclones. They can move inland before aircraft find a closed circulation. Sometimes their greatest threat is not wind, but water falling over mountains and low coastal plains. That geography is important because short-lived systems are easy to underestimate. Its satellite presentation can look lopsided, with thunderstorms displaced from the center and cloud tops pulsing unevenly through the day. Dry air may cut into one side, shear may expose the low-level swirl. Yet if the system drags tropical moisture onto land for 36 hours, the absence of a clean eye does not matter to the village downstream from a swollen river. The public tends to wait for symbols, a cone, a name, a category, a red hurricane icon placed over water. Meteorologists work earlier than that. They watch low-level vorticity, the tendency of air to spin near the surface. They watch mid-level moisture, sea surface temperatures, upper-level outflow, and the depth of warm water beneath the surface. Most of all, they watch vertical wind shear, because a developing cyclone cannot strengthen if the lower and upper parts of the circulation are being pulled in different directions. In 2026, shear was supposed to be the season's main suppressant. The anticipated El Niño pattern was expected to strengthen upper-level winds across the Atlantic, making it harder for storms to organize. That is the broad rule. The complication is that weather does not obey broad rules evenly across every basin, every week, every 12-hour forecast cycle. A hostile season can still contain favorable windows. A marginal environment can improve just long enough for thunderstorms to persist near a center. A system expected to move inland can slow, relocate, or briefly consolidate over water before crossing the coast. That is the gap. It is not a conspiracy gap, or a gap in observation, or a failure of science. It is the space between what can be responsibly forecast and what the atmosphere might still do. At 10%, the responsible message is low probability. At the coastline, the practical message may still be watched closely. Those two statements can both be true. The difficulty is that public attention often cannot hold both at once. Andrew's early life belongs in this conversation because it also occupied a gap. On August 20th, 1992, the storm almost dissipated. It had already been named, but its structure was poor. If viewed only through that moment, it looked like a system losing the argument against its environment. Then the surrounding pattern changed. The storm moved into conditions that allowed deep convection to wrap around the center. The pressure fell, the winds increased, the small circulation became violently efficient. The lesson is not that every weak disturbance is Andrew. That would be false. The lesson is narrower and more useful. Early weakness does not prove future safety. Forecasters know this, which is why their language remains open even when the numbers are low. A 10% formation chance is not zero. Marginally conducive does not mean impossible. Move inland does not eliminate impacts. The advisory text is designed to communicate uncertainty without exaggeration. But in the public mind, uncertainty often collapses into a binary. Either a storm exists or it does not. Either there is a threat or there is not. The real atmosphere lives between those categories. From space, the Bay of Campeche can look quiet even when the ingredients are present. Morning visible imagery may show scattered convection blooming over the water and collapsing by afternoon. Infrared satellite may reveal cold cloud tops, but not enough curvature. Surface observations along the Mexican coast may hint at falling pressure. while nearby buoys show only modest winds. One model run closes a low, another keeps it open. One ensemble member drifts north. Most take it west into land. The picture is not a verdict, it is a moving argument. That ambiguity rarely travels well online. A weak disturbance becomes either nothing or the beginning of the next catastrophe, depending on who is describing it. The careful middle ground is harder to package. Scientists detected a possible development area, not a hurricane. The name Andrew was historically relevant, not operationally available. The real warning was not that a Category 5 storm was already forming. The real warning was that early June had produced a test case in how risk is received before certainty exists. There is a reason that matters more now than it did in 1992. The observing system is vastly better. Satellites scan the basin constantly. Scatterometers estimate surface winds over the ocean. Microwave sensors can see structure beneath upper cloud decks. Aircraft reconnaissance can enter systems once operational thresholds are met. Models run in ensembles, producing not one future but a family of possible futures. Yet the human response chain still begins with attention. If a low probability is dismissed too early, even perfect instruments cannot force preparation into motion. The small system had found the most dangerous place in hurricane communication. Not the ocean, but the interval before people believe the ocean deserves attention. It was not strong. It was not named, it was not Andrew. But it had entered the gap where low probability, warm water, short lead time and public fatigue can coexist. In that space, the worst part is not what the disturbance is. The worst part is how quietly the first meaningful warning can pass across the screen. The warm water beneath the forecast. At the edge of hurricane science, the most important evidence is sometimes invisible from the beach. A person beside the Gulf can feel heat in the wind and watch low clouds move inland, but none of that reveals what matters beneath the surface. The ocean is not a painted blue sheet. It is layered. It stores energy vertically. A hurricane does not feed only on the skin of warm water at the top. It responds to how deep that warmth extends, how easily waves and wind can stir colder water upward, and how long the storm can remain over a reservoir that does not cool quickly when disturbed. That is why forecasters do not stop at sea surface temperature. A surface reading may show water warm enough to support tropical development, but a shallow warm layer can be exhausted by the storm's own winds. As the circulation strengthens, it churns the sea beneath it. If colder water sits close below, the hurricane draws it upward, weakening the heat supply. If warm water extends deeper, the storm can continue extracting energy, while its own waves try to disrupt the source. This is ocean heat content, and it has become one of the quiet measurements behind modern intensity forecasting. The Gulf of Mexico is dangerous in this respect because it can hide fuel in depth, not just on the surface. The loop current carries warm Caribbean water through the Yucatan Channel, into the Gulf, and out through the Florida Straits. At times, it sheds warm core eddies that drift westward as rotating pools of deep heat. A storm crossing one of those features can find an energy supply that resists cooling. That does not guarantee rapid intensification. The atmosphere still has to cooperate. Shear must be low enough. Dry air must stay out. The inner core must organize. But when a storm has structure and passes over deep warm water, the ceiling can rise quickly. Rapid intensification has a technical meaning. Operationally, it commonly means maximum sustained winds increasing by at least 30 knots in 24 hours. 30 knots sounds abstract until translated into damage potential. It can move a storm from manageable to dangerous in a single forecast cycle, or from dangerous to catastrophic while emergency officials are still coordinating evacuations. The problem is not simply stronger wind, it is time. Rapid intensification compresses decision-making. Andrew remains one of the clearest examples of that compression. After struggling in the central Atlantic, it entered a more favourable environment and strengthened sharply before reaching the Bahamas and South Florida. Its small core intensified with brutal efficiency. The region that would receive the worst damage did not experience a slow, gradual build-up of public understanding over many days. The final leap in intensity happened close enough to land that every hour mattered. The storm's compact size created another distortion. Communities outside the tight core could look at their conditions and misread the scale of what was coming for places only a short distance away. That becomes important later because modern forecasting has improved dramatically in track prediction, but intensity remains more difficult. A storm's path depends heavily on the surrounding steering currents, large atmospheric patterns that models can often resolve with increasing skill. Intensity depends on smaller, more fragile internal processes: eye wall formation, thunderstorm bursts near the centre, dry air intrusions, vortex alignment, ocean mixing, and shear changes. A model can identify the general road a storm will take, while still struggling to determine how powerful the engine will become before landfall. The Bay of Campeche disturbance sat at the far weaker end of that spectrum. It was not a hurricane waiting beneath a disguise. The official probabilities were low for a reason. Marginal conditions and an expected movement into Mexico limited the development window, yet the same physical principles applied. Warm water was present, moisture was present, a broad low could form. If thunderstorms persisted near the centre for long enough, the system could become more coherent before crossing land. Even a short burst of organisation can alter rainfall distribution, coastal winds, and public urgency. Here is the uncomfortable part. Coastal populations often respond to category, but category is only a wind scale. It does not measure rainfall, storm surge, inland flooding, or the speed at which a system changes. A weak tropical storm can kill through freshwater flooding. A Category 1 hurricane can produce life-threatening surge if its wind field is broad and the coastline funnels water efficiently. A major hurricane can be survivable in one neighbourhood and devastating in another because elevation, building quality, exposure, and timing differ block by block. The number is useful, but never the event. Ocean heat deepens that problem because it can change the event after people think they understand it. A forecast issued in the morning may describe a storm at one strength, while the ocean and atmosphere spend the next 12 hours building a different one. Hurricane Ian in 2022 offered a recent example of how forecasters watched a storm cross high ocean heat content and low shear while rapid intensification probabilities increased. The science was not blind to the risk. The difficulty was the narrowness of the clock. A similar pattern has appeared in storm after storm. Katrina strengthened over the Gulf before its 2005 landfall era, became synonymous with levee failure and catastrophic flooding. Michael intensified into a Category 5 hurricane before striking the Florida Panhandle in 2018. Laura, Ida, Ian, and others forced the same question into emergency management briefings. How do you move people, harden facilities, and communicate danger when the most consequential strengthening occurs near the end? The answer is not to treat every weak disturbance as a future disaster. That would exhaust public trust and distort the evidence. The answer is to recognise which ingredients deserve attention before a name exists. Deep warm water is one, low shear is another. Moist air, slow movement, and proximity to land can turn a weak system into a practical emergency, even without dramatic wind. A disturbance in the Bay of Campeche may never become a hurricane, but if it feeds moisture into terrain and coastal plains, the absence of an eye does not spare anyone downstream. So the warm water beneath the forecast was not a prophecy, it was a condition. It reminded forecasters that the ocean stores possibilities below what satellites first reveal. It reminded coastal residents that early season systems can be messy and consequential without becoming famous. And it sharpened the central lesson of Andrew's legacy. The atmosphere does not need a long warning to create a defining event. Sometimes it needs only a narrow window, a deep reservoir, and a coastline that believed the forecast had already told the whole story. The warning hidden in the weak system. The advisory did not sound urgent. It began with geography, then possibility, then restraint. A tropical wave was near the Yucatan Peninsula. A broad low could form over the Bay of Campeche on Friday. The environment was only marginally conducive. The system should move inland over eastern Mexico late in the weekend. Formation chances were low, 10% through 48 hours and 10% through 7 days. That is language designed to prevent overreaction. It does not close the door completely, because forecasters cannot close a door the atmosphere has left cracked. But it also does not pretend the evidence is stronger than it is. The disturbance had not organised into a tropical depression. It had not earned a number. It had not reached the threshold where advisories, forecast cones, or watches would be issued. On the official map, it was a shaded area and a percentage. To the public, a percentage can feel like a dismissal. 10% sounds small enough to ignore. Marginally conducive sounds like almost nothing. Expected to move inland sounds like the ocean will run out of time. Yet each phrase is doing specific work. A low chance is not a declaration of safety. It is a measurement of likelihood under the conditions available at that moment. Marginal conditions are not hostile conditions, they are conditions near the edge. Inland movement does not erase rainfall, mudslides, or coastal squalls. The warning is hidden in the grammar. This is how early tropical risk often appears before it becomes recognisable. It arrives as conditional language. It depends on whether thunderstorms persist. It depends on whether the circulation closes. It depends on whether shear relaxes for long enough. It depends on whether land interaction disrupts the centre or merely nudges it. The first notice is rarely cinematic. It is a paragraph written at a forecast desk in Miami, shaped by satellite frames, surface data, model output, and experience. The National Hurricane Center has an entire category for systems that have not yet become tropical cyclones but may still threaten land. Since 2017, it has been able to issue advisories on potential tropical cyclones when a disturbance is expected to bring tropical storm or hurricane conditions to land areas before it has technically become a cyclone. That change was not cosmetic. It recognized a problem in the old system. Warnings used to depend on formation. But coastlines do not care whether a circulation meets a strict definition before the wind arrives. A tropical cyclone is not just a mass of thunderstorms. It is a closed circulation, organized around a surface center, drawing energy from warm water and latent heat released by condensation. Before that structure exists, impacts can still be approaching. Heavy rain can spread across land. Squalls can reach the coast. Seas can build. Emergency managers may need to act before the atmosphere finishes satisfying the definition. The potential tropical cyclone system was created for that uncomfortable interval. It allows forecasters to issue the full advisory package, including track and intensity forecasts, even when the disturbance has not completed its transition. In practical terms, it gives the warning system permission to move before the storm is officially born. The scientific threshold and the public safety threshold are not always the same. That is the point. The Bay of Campeche disturbance in June 2026 had not reached that stage. It remained a low probability area in the tropical weather outlook. No tropical cyclone advisories were in effect. No watch or warning line had been drawn along a coast for that system. That fact should be stated clearly because precision matters. But the existence of the potential tropical cyclone category tells us why forecasters are careful with systems near land. A disturbance does not need a name to become operationally relevant. Look at the timing of watches and warnings, and the logic sharpens. A hurricane watch means hurricane conditions are possible, typically issued 48 hours before tropical storm force winds make preparation difficult. A hurricane warning means those conditions are expected, usually 36 hours before the onset of tropical storm force winds. The clock is not set by the arrival of the strongest winds. It is set by the moment preparation becomes dangerous. The public often waits for the worst part. The warning system is designed around the moment before ordinary movement stops being safe. This is one reason weak systems can be underestimated. Their first hazards are not always dramatic. A grey sky lowers over the coast. Fishing boats return early. Rain begins in uneven bands. Streets that flood every summer flood again, and at first, nothing about it feels historic. Then the same rain continues longer than expected. Ditches fill. Rivers respond slowly, then all at once. In low coastal communities, high tide meets runoff and nowhere drains properly. The category never appears, but the damage does. Andrew teaches a different side of the same warning. It was a named storm, then a weak storm, then an extremely violent hurricane. Its danger came from intensification, not ambiguity. But the early lesson overlaps with the Bay of Campeche problem. What matters most can develop after the first impression has already settled. On August 20th, 1992, Andrew looked fragile. 4 days later, South Florida was inside a Category 5 landfall. No serious meteorologist would claim every weak disturbance deserves that comparison. The value of the comparison is narrower. It shows how poor a first impression can be when the atmosphere is still changing. The weak system in 2026 exposed an interpretive failure. Scientists saw a low chance and kept watching. Many outside the forecast world saw a low chance and stopped watching. Between those reactions is the entire problem of hurricane communication. The official forecast must avoid exaggeration, because credibility is a finite resource. but the public needs enough concern to take early information seriously before certainty arrives. Too much alarm creates fatigue. Too little emphasis creates delay. There is no perfect phrasing for that balance. If the language is too strong, a 10% disturbance sounds like a false emergency. If the language is too quiet, a coastal population may miss the reason it was mentioned at all. The forecast has to carry two truths at once. Most low-probability disturbances do not become dangerous cyclones, and a small fraction become important because they are close to land, moving through warm water, or capable of producing rain before wind defines them. That was the warning hidden in the weak system. Not that a hurricane had already formed, not that Andrew had returned, not that the forecast had failed. The warning was that the earliest credible signal of tropical risk can look small, technical, and easy to dismiss. By the time the language becomes unmistakable, the calendar has already moved, the shelves are already crowded, the roads are already filling, and the atmosphere has already taken its next step. The model saw different futures. In the quiet hours before a tropical system becomes obvious, the most crowded place in the storm is not the sky. It is the forecast screen. Lines appear over the Gulf in different colours, each one representing a possible version of the atmosphere. Some bend into Mexico, some hesitate over warm water, a few lift moisture northward toward Texas or Louisiana. Others never close a centre at all. To someone outside meteorology, the display can look like confusion. To forecasters, it is evidence. Weather models do not see the future. They calculate possible futures from an imperfect picture of the present. That starting picture is assembled from satellites, buoys, aircraft observations, ships, weather balloons, radar, surface stations, and numerical estimates over places where no instrument is directly measuring. The computer does not begin with reality. It begins with the best available analysis of reality. Then it applies physics forward in time. The problem with a weak tropical disturbance is that the first step may already be uncertain. Where is the centre, if there is one? Is the lowest pressure underneath the thunderstorm mass or exposed to one side? Are the winds turning at the surface, or only higher in the atmosphere? Is convection building near the circulation, or being blown away before it can organise? A hurricane has a defined structure. A tropical wave often has several competing hints of structure. Models must choose how to represent something that may not yet fully exist. That is why early guidance can split. One model may develop a closed low because it maintains thunderstorms over the warm Bay of Campeche long enough for pressure to fall. Another may weaken the wave quickly because shear stays strong. A third may generate rainfall but no cyclone. None of these outcomes has to be foolish. Each can come from a different treatment of moisture, land interaction, vertical wind, or small-scale convection that the model cannot resolve directly. The public often sees the result as disagreement. Forecasters see spread. That distinction matters. Disagreement implies failure. Spread implies uncertainty measured in multiple directions. An ensemble forecast is built around that idea. Instead of running the atmosphere once, the system runs many slightly different versions, each with small changes in the initial conditions or in how uncertain physical processes are represented. NOAA's Global Ensemble Forecast System, for example, generates multiple members to address uncertainty in observations and in the model itself. If most members show no development, forecasters take that seriously. If a small cluster begins strengthening the system, they do not ignore it. The question is not which line looks most dramatic. The question is whether the atmosphere is opening a pathway that more members begin to recognise over time. One isolated run showing a storm is not the same as a trend. A trend means repeated cycles of finding similar structure, similar timing, and similar steering. It means uncertainty is narrowing. Until that happens, the official forecast must remain disciplined. This discipline is visible in the National Hurricane Centre's model process. Hurricane specialists do not simply copy one computer run. They use objective guidance models, compare early and late model availability during the forecast cycle, weigh consensus aids, examine satellite trends, and apply human expertise. Consensus matters because no single model is consistently best for every storm, every basin, and every stage of development. The official forecast is a synthesis, not a surrender to machinery. But synthesis takes time, and near land, time is the resource most easily lost. A disturbance in the central Atlantic can wander through uncertainty for days without directly threatening anyone. A disturbance in the Bay of Campeche has less room. If it organises late, there may be only a narrow window between recognition and impact. Model uncertainty then becomes more than a scientific condition. It becomes an emergency management problem. Consider what local officials need from the forecast. They need to know whether shelters should open. They need to know when to warn hospitals, ports, schools and coastal industries. They need to know if rainfall will be isolated or widespread, if roads might flood, if tides will worsen drainage, if power crews should be staged. These decisions are expensive before the storm and politically scrutinised after it. Acting too early can look unnecessary. Acting too late can cost lives. The models do not make those decisions. They create the probability field inside which those decisions must happen. Andrew showed the cost of underestimating the late stages. Its track forecast improved as the storm approached, but its intensity rose into a category of destruction that exceeded what many structures were prepared to handle. In 1992, the limitations were not only computational, they were institutional, architectural and behavioural. People believed buildings would perform, many did not. People believed preparation time was sufficient, for many it was not. A forecast can be technically impressive and still meet a society that has not converted information into protection. Modern models are far better than the tools available then, but the hardest problems have not vanished. Rapid intensification remains difficult because it depends on small inner core processes and precise ocean-atmosphere coupling. NOAA research has repeatedly identified intensity forecasting, especially rapid intensification, as one of the most challenging parts of tropical cyclone prediction. The track can be increasingly confident while the strength remains uncertain. That is a dangerous combination because the cone can make the future look fixed even when the damage potential is still changing. The cone itself is often misunderstood. It represents historical track error around the forecast centre, not the size of the storm, not the edge of impacts, and not a guarantee that danger stops outside the shaded area. Rain, surge, and tornadoes can reach far beyond it. For a weak or developing system, the cone may not even exist yet, because advisories have not begun. The public, trained to wait for that graphic, may be unaware that forecasters are already studying a set of competing futures behind it. By June 2026, the Bay of Campeche signal belonged to that hidden stage. The official odds stayed low. Most plausible futures were unimpressive. The system was expected to move inland before major development. Yet the models still mattered because they revealed what forecasters were actually watching. Not a single predicted storm, but the possibility space around one. If that space remained closed, the disturbance would become rain and memory. If it widened, the conversation would change quickly. That is the uneasy truth behind the model spread. The danger is not that computers disagree. The danger is that the atmosphere sometimes decides late, and humans prefer early certainty. Forecast models can show many futures, but coastal decisions often have to be made before one future wins. The coastline built for yesterday's storms. South Florida rebuilt under a sky that looked unchanged. The same afternoon heat settled over rooftops. The same palms bent in sea breeze along Biscayne Bay. Traffic returned to US 1. Construction trucks lined up beside stripped subdivisions. From a distance, recovery could be mistaken for replacement. A house went back where a house had stood. A school roof was repaired. Streetlights returned. The map looked familiar. The inspection revealed something less comforting. Andrew had not merely damaged South Florida. It had exposed the weakness of an entire building culture. Before the storm, Florida did not operate under one unified statewide building code. Rules varied across jurisdictions. Enforcement varied with them. In some places, plans on paper and construction in the field had separated quietly over years of growth. Roof connections, gable ends, garage doors, windows and load paths became technical phrases after the disaster. But during the storm they had been failure points. Wind found them without needing to know their names. A hurricane attacks a building by sequence. First, pressure rises against the walls, then the roof tries to lift. Openings fail, sometimes from debris, sometimes from pressure, sometimes from poor protection. Once wind enters, the house is no longer resisting from the outside only. It is pressurized from within. The roof system can detach. Rain follows the wind. Ceilings collapse. The structure may remain standing, but the home has already been lost. Andrew made that sequence visible across neighborhood after neighborhood. The storm's landfall near Homestead on August 24, 1992, brought Category 5 winds into a rapidly developed region. Later analysis set Andrew's South Florida landfall intensity at 165 miles per hour. The compact core concentrated the worst destruction south of Miami, which spared the densest urban centre from the eyewall's full force. Andrew was catastrophic, and yet it was not the maximum scenario for the region. Had the track been farther north, the damage field would have crossed a larger share of Miami-Dade and Broward's urban fabric. One slight shift would have placed more hospitals, high-rises, older apartment blocks, and infrastructure inside the worst winds. Afterward, reform moved through Florida in stages. South Florida tightened requirements first. Miami-Dade and Broward became associated with some of the strongest windborne debris standards in the country. The statewide Florida Building Code took effect in 2002, replacing the older patchwork with a unified framework. Stronger roof attachments, impact protection, improved inspections, and wind load standards became part of the new vocabulary of hurricane survival. The lesson was written into law because memory alone could not be trusted to hold it. Yet codes are not time machines. They govern new construction and major renovations more cleanly than they transform the entire existing building stock. A house built before Andrew may still stand on a quiet street, painted, landscaped, insured, and occupied, while carrying older assumptions inside its roofline. A condominium can meet the standards of its era and still face a modern hazard profile. Manufactured housing, older rental units, aging low-income neighbourhoods, and informal repairs all sit unevenly inside the promise of stronger standards. The code improved the future, but it did not erase the past. Population changed the equation as well. Florida did not stop growing after Andrew. Coastal counties expanded, inland suburbs pushed outward into former farmland and wetlands. Roads widened, shopping centres, logistics parks, retirement communities, apartment complexes, and gated subdivisions multiplied across areas that had once held fewer people and fewer insured structures. A storm crossing the same region today would not be striking the same society. Even where buildings are stronger, there are more of them, tied together by longer supply chains, denser electrical networks, more vehicles, more elderly residents, and more people unfamiliar with the last great local disaster. This is the quieter vulnerability of 2026. It does not appear as a swirl on satellite. It exists in roof permits, drainage maps, evacuation zones, mortgage documents, hospital generator plans, and the private decisions of people who have never had to leave before. The coastline has been hardened in some places and made more crowded in others. Progress and exposure grew together. Storm surge adds another layer. Andrew is remembered primarily as a wind catastrophe, but many modern landfall scenarios are governed by water. Surge does not care whether a building has impact glass if the first floor is below the height of moving seawater. Rainfall does not consult the roof code before entering an overwhelmed drainage system. A stronger envelope can protect against windborne debris and still sit in a neighbourhood where flood depth determines the final loss. In hurricane planning, the building is only one part of the system. The road to reach it, the substation that powers it, the canal that drains it, and the hospital that serves it are part of the same exposure. That becomes important when a weak tropical disturbance enters public conversation. People hear that a system is unlikely to develop and imagine the main danger has been removed. Emergency planners see a different landscape. They see communities where even a disorganized rain event can create problems if the ground is saturated or drainage is poor. They see coastal infrastructure that functions well in normal weather, but loses redundancy under compound stress. They see residents who rely on a narrow preparation window because work, money, transportation, age, or disability limits their options. The phrase built for yesterday's storms is not an insult to engineers. It is the reality of a moving target. Building codes improve after disasters, but disasters also change. Research advances, construction improves, and then the coastline fills with new value. Sea levels rise relative to land in many communities, rainfall extremes intensify in some regions, and the memory of past storms thins as newcomers arrive. A standard written after one catastrophe may perform well against wind, and still be tested by water, duration, heat after power loss, or evacuation logistics. Andrew forced Florida to become more serious about wind. That achievement matters. Homes built under stronger codes have shown better performance in later hurricanes, and the difference is not theoretical. The reforms saved losses, reduced failures, and gave later generations a stronger starting point. But the central question in 2026 is not whether the coastline learned anything. It did. The question is whether the lesson kept pace with the exposure that followed. A storm does not strike a building code. It strikes everything constructed under old codes, new codes, exceptions, renovations, shortcuts, aging materials, and uneven enforcement. It strikes the decisions made by people who believe the worst local storm belongs to history. Along the Gulf and Atlantic coasts, the next dangerous system will meet not just warmer water and forecast uncertainty, but a built environment assembled across decades of confidence. Andrew changed the rules. The coastline kept building. The evacuation clock starts before the panic. The first cars do not leave because the wind is blowing. They leave while the sky still has colour, while gas stations are open, while television crews are standing calmly in parking lots beside stacks of bottled water. Evacuation, when it works, begins before the storm has given people emotional proof. That is the part the public often resists. The official clock starts in an atmosphere that can still look manageable. A hurricane watch is not timed for the moment hurricane winds arrive. It is issued because preparation becomes difficult once tropical storm force winds begin. 48 hours sounds like a generous warning until the hours are filled with work schedules, school closures, fuel lines, bridge restrictions, nursing home transfers, hospital decisions, pets, prescriptions, and the slow physics of traffic. A hurricane warning, normally issued 36 hours before the expected arrival of tropical storm force winds, sounds more serious, but by then, the practical window has already narrowed. The strongest winds may still be far offshore. The safe movement of people may not be. That detail matters because evacuation is not a single decision. It is a sequence of smaller decisions made by thousands of households and institutions at different speeds. A family with a car, savings, and relatives inland can leave quickly. A resident in a high-rise who depends on an elevator, a caregiver, or medical equipment faces a different clock. A hospital cannot simply close its doors and drive away. A jail, a nursing home, a dialysis clinic, an assisted living facility, and a coastal school district each move on timelines that began long before the public recognizes urgency. Emergency planners use the phrase clearance time for this reason. It is the estimated period needed to move an at-risk population out of danger after an evacuation order is given. The term sounds administrative, but it contains the whole vulnerability of a coastline. Roads have limits, intersections have limits, bridges have limits, fuel supplies have limits, human patience has limits. The map may show a clean route inland, but a highway during evacuation is not a line. It is a system of vehicles, ramps, bottlenecks, stalled engines, weather bands, police decisions, and people changing their minds. Andrew exposed a version of this problem in 1992. The storm was compact and fast-moving, and the worst wind struck south of Miami before dawn on August 24th. Many residents had prepared, but the final intensity and exact destruction field still overwhelmed the built environment and the public sense of what the storm could do. Some people evacuated, some stayed because they were outside the most obvious danger zone. Some had survived previous storms and assumed this one would be comparable. That assumption became part of the disaster. The question is why people wait. Not because they are irrational. Often they wait because every evacuation has a cost. Leaving means money spent on fuel, hotel rooms, food, missed wages, and uncertainty about return. It means deciding what to carry and what to abandon. It means trusting that the risk at home is greater than the risk on the road. After storms that curve away, weaken, or arrive with less local damage than expected, people remember the inconvenience more clearly than the avoided danger. The next warning competes with the last false alarm in their private memory. Forecast improvement has not removed that conflict. Better track forecasts can narrow the area of concern, but they also create sharp boundaries in the public mind. A household just outside a cone may feel excluded from risk. A family inside the cone may wait until the center line points directly at them. Storm surge zones, rainfall forecasts, and wind fields tell a broader story, but the public often compresses everything into one graphic. The cone becomes a permission slip to worry or not worry. This is dangerous near the Gulf Coast because geography can shorten the response time. Some communities sit behind long bridges, narrow causeways, or road networks that were not designed for mass movement at once. Barrier islands depend on access routes that may close before the worst conditions arrive. Low-lying neighbourhoods may flood from tide and rain before hurricane winds reach full strength. If officials wait for perfect certainty, they may lose the clearance window. If they act early, they risk moving people for a storm that changes track. There is no clean solution inside that trade-off. The forecast is probabilistic. The order is binary: leave or stay, open shelters or do not, suspend school or continue, close a port or keep commerce moving. The atmosphere rarely gives the kind of certainty that public officials would prefer before imposing disruption on an entire region. So the evacuation clock begins in doubt. Weak systems complicate it further. A developing disturbance may not yet have a forecast cone, it may not have a name. It may still carry low formation odds while producing heavy rain or rough coastal conditions. If it strengthens close to land, official language can escalate faster than public behaviour. The first advisory may arrive after some people have already decided the event is minor. Once that mental category is set, it can be difficult to reverse. People do not update risk as quickly as weather models do. The vulnerable are affected first. Older residents may need transportation assistance. People without cars depend on buses, neighbours, or local pickup points. Workers in hourly jobs may not leave until employers close. Families living paycheck to paycheck may delay because evacuation requires cash before reimbursement, if reimbursement ever comes. Undocumented residents may avoid official shelters out of fear or uncertainty. Tourists may not know evacuation zones at all. Every hurricane plan assumes movement. Many lives are lived with limited ability to move. A storm does not have to be Andrew to reveal this. A smaller system can still test evacuation behaviour if it arrives with short notice, uncertain intensity and heavy rain. The real pressure point is timing. Wind begins before landfall. Surge rises before the eye arrives. Roads flood before the storm reaches its maximum local force. Nightfall changes driving. Power loss changes communication. The end of preparation rarely announces itself with ceremony. It arrives as a closed bridge, a gas station without fuel, a road underwater, a county message saying conditions are no longer safe for responders. By then, panic is not useful. It is only late energy. The most effective evacuation is almost invisible on camera. It is cars leaving while the streets still look ordinary. It is a caregiver moving a patient before rain begins. It is a county activating buses before residents feel afraid. It is a family choosing inconvenience while the forecast still has uncertainty. In hurricane country, that early discomfort is part of survival. The storm's violence may begin offshore, but the race against it starts earlier, inside the hours people are most tempted to waste. The part of the storm people misread. The most familiar hurricane image is the one that often tells the least complete story. A number appears beside a storm's name, and the public begins to sort danger by category. Category 1 feels survivable, Category 3 feels serious, Category 5 becomes a symbol of total force. The scale is simple, portable, and easy to broadcast. It also measures only sustained wind. That limitation is not a flaw hidden in the system. It is stated plainly in the name, the Saffir-Simpson Hurricane Wind Scale. It does not calculate storm surge. It does not measure rainfall. It does not describe how wide the wind field is, how slowly the storm moves, how saturated the ground already is, or how far inland the water will travel after landfall. It tells people something important, but not everything dangerous. A hurricane is not a single hazard. It is a moving collection of hazards arriving at different times in different places with different consequences. Wind can destroy roofs and transmission lines. Surge can lift the ocean over roads, marshes, seawalls, docks, and first floors. Rain can turn inland rivers into delayed disasters long after the eye has weakened. Tornadoes can spin out in outer bands while the centre remains offshore. Rip currents can kill swimmers hundreds of miles from the landfall point. The category number compresses all of that into one piece of information, and the compression can mislead. Storm surge is the most visually deceptive of the major hazards because it begins as a change in height. On a calm day, the difference between dry pavement and catastrophic flooding can be only a few vertical feet. Coastal residents may look at a seawall, a beach road, or a canal, and imagine the boundary is more permanent than it is. During a hurricane, wind pushes water toward land, low pressure raises the sea surface slightly, waves build on top of elevated water, and the coastline can funnel the surge into narrower spaces. A bay, an inlet, or a shallow shelf can turn the ocean into a horizontal force. The water does not arrive like a clean wall. It seeps, rises, overtops, pulses, and then begins carrying debris. Cars float before houses fail. Doors jam, electrical systems short, stairwells become currents. The difference between standing water and moving water is the difference between inconvenience and force. A person who could walk through ankle-deep water in the morning may be trapped by chest-deep moving water at night. That transformation can happen while the storm's wind category is weakening. Rainfall tells a slower story, and for that reason, it is often underestimated. A hurricane moving quickly may deliver violent weather and leave. A weaker tropical storm that stalls can produce far more water. Inland flooding can unfold away from cameras focused on the coastline. Rivers respond after the heaviest rain has already fallen. Mountain terrain can concentrate runoff into narrow valleys. Low-gradient coastal plains can hold water for days because drainage has nowhere to go. When the public says a storm was only a tropical storm, hydrology may already be proving otherwise. This is why the Bay of Campeche disturbance mattered even without a name. Its wind potential was limited by marginal conditions and land interaction. But tropical moisture does not need a named centre to create rainfall problems. A broad, disorganised system can pull warm, humid air northward and feed repeated bands of rain over the same region. If the disturbance moves inland over Mexico, terrain can enhance rainfall and raise the risk of flash flooding and mudslides. If moisture spreads into Texas or the northern Gulf Coast, the threat may become less about cyclogenesis and more about where rain trains. The public does not always track that distinction. People understand wind because wind is audible. It rattles shutters, bends trees, tears signs loose, and appears in dramatic footage. Water can look almost ordinary until escape routes are gone. A flooded street looks shallow until the curb disappears. A drainage ditch looks manageable until it merges with the road. A river looks high but stable until upstream rain reaches the gauge. By the time the danger is visible to an untrained eye, the safe decision may already be behind the clock. Andrew, in this chapter, serves as a contrast. It was a wind catastrophe, one of the defining wind disasters in American hurricane history. The eyewall struck South Florida with Category 5 intensity, and the damage field south of Miami revealed what extreme wind can do to a built environment. Yet Andrew's legacy has sometimes narrowed public imagination. When people think hurricane disaster, they often think of destroyed roofs, flattened neighborhoods, and wind speed. Those images are accurate, but they are not the full grammar of hurricane loss. Katrina in 2005 changed the national understanding in another direction. The storm weakened before landfall from its peak intensity, but its surge and the failure of flood protection around New Orleans created a catastrophe that cannot be understood by category alone. Harvey in 2017 made the rainfall lesson unavoidable, dropping extraordinary amounts of rain over southeast Texas after landfall and producing historic flooding. Ian in 2022 brought destructive surge to southwest Florida, while inland flooding continued across the peninsula. Each event forced the same conclusion from a different angle. Wind category is a chapter, not the book. That becomes the central communication challenge of 2026. Forecast offices can issue surge maps, rainfall outlooks, flood watches, excessive rainfall discussions, river forecasts, and local statements. The information exists. The problem is whether people assign it the same authority they assign to the category. A Category 1 hurricane approaching a surge-prone coast may require more urgent action than a stronger storm aimed at a less exposed shoreline. A tropical storm over saturated ground may deserve more concern than a hurricane expected to pass quickly offshore. The name and number can anchor attention in the wrong place. Emergency management has adjusted to this reality by emphasizing hazard-specific messaging. Evacuation zones are often based on surge risk, not wind category. Rainfall forecasts are issued with ranges and flash flood potential. Local National Weather Service offices translate basin-wide advisories into county-level impacts. Still, a single number travels faster than a nuanced warning. It fits in a headline, it fits on a thumbnail, it fits in memory. The storm people misread is not always the strongest one. It is the one whose most dangerous hazard is not the hazard they were watching. A weakening hurricane can still push the sea inland. A nameless disturbance can still flood a valley. A narrow eye wall can miss one city and erase another. A forecast can be accurate and still fail in the public mind if the audience hears only wind. The worst part of any hurricane is not always at the centre. Sometimes it is outside the category, waiting in the water. The storm that has not happened yet. By the time a hurricane becomes history, the images have already hardened. The broken marina, the missing roof, the neighbourhood filmed from a helicopter, the highway signs folded backward, the family standing beside soaked furniture on the curb. Disaster becomes visual after it is too late to prevent its first decisions. Before that, it is mostly administrative. A line of text in an Outlook, a briefing packet opened on a county computer, a pressure reading, a model ensemble, a fuel delivery schedule, a generator test at a hospital loading dock, a school district deciding whether buses can run safely tomorrow. The future catastrophe, if it comes, begins as paperwork and weak signals. That is why the 2026 conversation around Andrew was never really about Andrew returning. The name cannot return. It was retired after 1992, removed from the rotating Atlantic list because the damage and memory attached to it were too heavy for reuse. No official storm in 2026 will be called Andrew. That point is not minor. It separates evidence from atmosphere, science from viral shorthand, a forecast from a ghost. What scientists were watching in June was smaller, quieter, and more revealing. A weak area near the Bay of Campeche, a low chance of development, a season expected to be suppressed by El Niño. Nothing in the official language justified panic. At the same time, nothing in the official language justified sleepwalking through the first warnings of the year. The threat was not a monster already named on the map. It was the familiar American habit of waiting for certainty before acting on risk. Hurricane history is filled with that delay. Communities do not usually fail because nobody told them storms exist. They fail in the space between knowing and moving. Someone believes the forecast will shift. Someone remembers the last evacuation that wasted money. Someone thinks the category is too low. Someone outside the cone stops listening. Someone in an older house assumes codes protect them. Someone sees rain, not floodwater. The atmosphere does not need all of those mistakes. It only needs enough of them, in enough places, at the wrong time. Andrew's value in 2026 is not as a prediction. It is a scale marker. It shows how a quiet season can carry one unforgettable storm, how early weakness can precede violent organisation, how built environments can hide defects until wind inspects them, and how a small change in track can spare one city while destroying another. The lesson is not that every disturbance is Andrew. The lesson is that the public often identifies danger too late in the process. Modern forecasting has made extraordinary progress since 1992. Satellites are sharper, models are more sophisticated, reconnaissance data is better integrated, storm surge guidance, rainfall outlooks, and ensemble forecasts give officials a richer picture than earlier generations had. Yet better information has not solved the final weakness, because the final weakness is human conversion. Data must become attention. Attention must become preparation. Preparation must begin before fear makes it obvious. The most dangerous storm in any season is not necessarily the strongest one measured by wind. It may be the one that arrives where memory has faded, where newcomers do not know evacuation zones, where older buildings remain outside modern assumptions, where drainage is already near capacity, where the forecast sounds mild until the hours are nearly gone. It may be a hurricane, or a tropical storm, or a nameless disturbance that never receives the symbolic weight of a category. The atmosphere has more ways to create loss than the public has habits for recognizing. That is the part of 2026 worth holding on to. A below-normal seasonal forecast does not cancel the coastline. A low-probability disturbance does not become harmless by being statistically unlikely. A retired name does not have to appear on an advisory to remain relevant. The warning is not contained in one storm. It is spread across the system that will face the next storm. The roads, the houses, the codes, the forecasts, the emergency messages, and the private choices made long before landfall. Imagine the Gulf in the final hours before a real threat becomes obvious. The water is warm under a grey sky, offshore platforms report shifting winds. Radar begins to show curved bands that were not there the night before. Meteorologists compare satellite loops and notice convection persisting near a centre that had been poorly defined. County officials revise their morning briefings. Local stations update graphics. Grocery stores fill. Phones buzz with alerts that sound more serious than yesterday's. By then, the storm has not changed alone. The public has finally caught up to what forecasters were watching. That lag is the true subject. Not fear, not spectacle, not a claim that a historic hurricane is secretly forming. The real story is the narrow interval between detection and belief. Science can identify uncertainty. It can describe possible futures. It can issue watches before the worst winds arrive and warnings before preparation becomes unsafe. But it cannot force a coastline to respect a low number, a messy satellite image, or an advisory that lacks dramatic language. If a major hurricane does form later in 2026, it will not need to resemble Andrew to expose the same old problem. It will only need a coastline with too much confidence and too little time. If the season stays quiet, the lesson still remains, because quiet years are part of the trap. They train people to associate calm with safety, and safety with postponement. Then, eventually another storm arrives to test what was postponed. The storm that has not happened yet is not on the map. It has no name, no cone, no landfall point, no damage estimate. It exists as a possibility inside warm water, vulnerable buildings, crowded coasts, forecast uncertainty, and public memory. That may sound abstract until the first real advisory appears. Then the abstraction becomes a clock. Andrew cannot come back. That is the factual truth. But the conditions that made Andrew so consequential were never retired. They remained scattered through the coastline, waiting for the next system capable of finding them. The storm was not Andrew. The name could never return, but the warning behind it never disappeared. A weak signal, a quiet forecast, a coastline still carrying old vulnerabilities, and a public waiting for certainty before taking risks seriously. That is where the real danger begins. If you found this video useful, subscribe for more deep investigations into the science, history, and hidden patterns behind real-world disasters. And before you go, tell us in the comments, would you prepare early for a low-probability storm, or wait until the warning becomes impossible to ignore?